Here we're going to take a look at the next step, which is Fourier series. So let's do a little recap here. We started from, we're looking at the heat equation, right? That's just our example. We're looking at boundary conditions in which the ends of a rod are 0 degrees, as we can see right here. Step 1, we separated the variables. We got two equations, a second order ODE and a first order ODE. Next step, we solved the boundary value problem. We got our eigenvalue and our eigenfunction, our x sub n. Step 3, we solved for t sub n, which is right here. Step 4, we found our fundamental set of solutions, which is right here. We then found the general solution, which is right here. So now in step 5, we're going to use this general solution in a given initial condition. And you might be thinking, well, what's an initial condition? We didn't do that yet. Well, say this is our initial setup here, correct? But we're also going to have an initial condition. So we have a rod, right? Let me just write this out first. It'll make more sense. Let me think what it should be. It should be something like times 0. Okay, so we have our 0 degree ends, right? When x is 0 and when x is L, temperatures are 0 on the rod. Okay. What about the middle of the rod, for example? For any value of x in between those two values. At time 0, what's the temperature of the rod? Well, let's say it started out as a value, right? You could say it starts out as 25 degrees. The whole rod is 25 degrees. But typically that's not true, because typically what the heat equation usually looks at is heat dissipation, right? So that's typically represented by a function. So we can say, at this point x, the temperature here is represented by this function at time 0, right? So that's what would be our initial condition for this problem. Okay, so from the last problem, we have our general solution up here. I've wrote it up here. What we're going to do is we have u of x of t. Now we want to find ux of 0. So we're going to find ux of 0. We're going to rewrite this. So all we're doing is plugging in 0 in for t, right? This all stays the same. But this part, you can see here that we have the t's over here. When we plug in 0 for that, we get e to the 0. That becomes 1. So then this is just this right here. Well, remember, it equals f of x, right? So this is what we're looking for here. This is what we need to start off our Fourier series right here. So before I go any further, let's take a look at the general solution for the general form for a Fourier series. Okay. Let me see here so I make sure it's correct. Okay, so we have f of x. Now some people do write this differently. Like it might just be a naught, not a naught over 2, but a naught's a constant. It's not dependent on n. If you remember from our boundary value problems, we had a few eigenvalues that were like this, right? That's exactly where this comes from. We can have a cosine component, and we can also have a sine component, which is what our current one has, right? But so this is the basic form for a Fourier series. Now from this, we can solve for these coefficients. So a naught, a sub n, and b sub n are known as Fourier coefficients. Now I already have a video out deriving these coefficients, but typically, we don't worry about that. We're just going to go right into memorizing them. So I highly recommend just memorizing these. Where a sub naught, let me look here. I don't remember these off the top of my head. A sub naught is 1 over L integral negative L to L f of x d of x. And a sub n is 1 over L integral negative L to L f of x cosine n pi x over L dx. B sub n is 1 over L negative L to L f of x sine n pi x over L dx. So basically all you would do, you would solve for each one of these, right, given an f of x. So say f of x is 25, you just plug in 25 into here. Solve, we know the length, we've given a length of a rod, say it's like 5. So length of a rod is 5, f of x is 25, you plug those in, solve for b sub n. Once you get b sub n, you go back up to your general solution, which is right here, and you just plug in your coefficient, and that's your solution. Okay, so you use the initial condition to get this right here, okay, to get the constant. But now you're like, well, what's this form right here, right? Well, this we just used to write it like this. And it's very important that you do write it like this. A lot of people initially, for the heat equation especially, will think, oh, I can just skip this part. No, actually, you can't skip this part. You have to write this out because, obviously you have to get rid of this e over here. But in order to solve, we can see that this is a sine series, right? But sometimes you end up with something like, where you could end up with something like this, where you might have a hyperbolic trig function next to it, and you'll actually have to move that over to the other side here when you solve for your coefficient. So some weird things happen. So make sure that you always use the initial condition to solve for f of x, and then we use this right here to solve for the coefficient. Once we get the coefficient, we plug it into the general solution, get our answer. So looking at this right here, this is a pretty straightforward problem because we're not given any numbers, right? So there's not much we can do here. So for this problem, we have k sub n as our variable. So now looking at the general solution, the general form for Fourier series, k sub n would correspond to this term right here. Because you see we have this term right here. Those are the same. So you can kind of think of k sub n being b sub n. So for this problem, our k sub n would be 1 over L integral negative L to L f of x, which is just f of x for this problem, times sine n pi x over L dx. That's the answer. If we had numbers, we would integrate this, right? So then you just go ahead and plug back into the general solution, which would be u of x of t is equal to series n equals 1 to infinity k sub n, which is 1 over L integral negative L to L f of x sine n pi x over L dx times, yeah, I can write it like this, I guess. Times sine n pi x over L let me move this over so we have some space. I'm just going to copy this times this. Right? Yeah, I still don't have enough space. Is that easy enough to read? Well, that's the answer right there to our general solution. So this would be the solution. And then what this means, basically, wait, yeah, so because this is a series, right? And it's a sine series, we're going to, man, typically, like, this is just a general view. It might not be exact to this one, like what I was explaining before. So you look at n equals 1, it'll look something like this for n equals 1. Right, as you go up an n, you'll end up with something like this. It kind of goes up higher. Little oscillations. You know, there'd be bigger oscillations. It'll look like this. It's down. It's up. It's down. You know, but then we start to get more. We'll start to get like more defined, like start to get smaller and smaller, because as it converges to a solution, it's smaller and smaller, right? And it'll get smaller and smaller, and eventually it'll reach a solution, of course, right? This right here represents that solution. But of course, if you run this like numerically in like a solver, of course you're never going to be able to run it for all values of n, so you're never going to get that solution. So it's typically considered, even though this is the exact solution, it can still be considered an approximation. And you can kind of see why. But yeah, that's a decent overview of like Fourier series, how to solve it. Of course, there's more that goes into it, and I'm going to get more into that as we go along. But first, I have 5 pretty basic examples of a Fourier series. Just looking at starts with different functions that are given to us. We sketch the function, and then find the Fourier series for the given function based on the interval that's given, the interval x. So then we know I have 5 examples of those, which goes through a bunch of different cases of what could happen. And then I also have, I forget what they're called now. Oh yeah, it's called a half range expansion. Basically, if you have a function that's not periodic, or that doesn't, how do I explain it? I guess it could be periodic, but I guess it's kind of like if the function doesn't span over a full period, if like it only spans over half of a period. Basically, say like a period is from negative L to L, and say your particular function only goes from L to L, well, you might have to make what's called either an even or odd extension on the function in order to solve the Fourier series. So we're also going to look at that after some examples. So I have 5 examples, and then probably at a little video on half range extensions and then an example. So I'll see you for that stuff. Hope you enjoyed the video.